So to all the participants, so the plan will be the following, that during the lecture, you are encouraged to type your questions. And if the speaker agrees, we can take up those questions around the halfway stage. If there are very quick questions and if the speaker agrees, then he or she can answer to those. Otherwise, at the halfway stage, if the speaker agrees, we can take up. And then there is a dedicated session at the end of the lecture where you can raise your hand or type your questions. Depending on the time, we will take up all this. Would that be fine, Amitabh?
Yes, Srijit. Actually, if there are short questions, students can stop me in between. That is perfectly okay. But if there is a longer discussion, then of course we can postpone it to a later discussion session.
Okay. So then you may start.
Okay, so let me start by thanking Srijit and Anjanda for and all the other organizers for inviting me to this event. I have been to IIIT Allahabad in person a couple of times, but this is an online event. Okay, I look forward to visiting IIIT Allahabad again. So this is the outline of my lecture. So I have been asked to give a sort of pedagogical lecture on Bondi-Sachs formalism. So this is the outline. So I will start with a very broad introduction to the subject, preliminaries. Then I will explain why general relativity is so different from electrodynamics, and we need sufficiently detailed formalism to address issues related to asymptotic structures of space-time. Then I will discuss there are various different approaches to address this question. And in particular, Bondi-Sachs formalism is one approach. And then I will explain the Bondi-Sachs formalism. So this is the third and the main part of the talk today. So then I will discuss gravity in Bondi gauge. And gravity in Bondi gauge is a sufficiently rich topic. There are many aspects. So in today's lecture, I will discuss the so-called Bondi news and the Bondi mass. And in the next lecture, I will discuss other things. Okay, so here is the, let me start. Okay, are you able to see my screen properly? Is the size?
Actually, there's this message, share the document on the slide. So if you can just click somewhere, it will go away. It's fine.
Yeah, is the size okay?
I think it's okay for me. I think it's okay.
Okay. So let me start with the preliminaries. So in general relativity, we are often interested in studying properties of isolated systems. So we want to study properties of a star, let's say. But if you want to study the properties of the star, we have to worry about, let's say we want to study the properties of the star sitting at the Earth. Then if we have to worry about the curvature of the Earth, or if we have to worry about the effect from the distant galaxies, or if we have to worry about the cosmological curvature of the space-time, then we will not be able to make much progress. Because in practice, physical system is not truly isolated. There are all these effects present. But in a precise sense, if you want to study the properties of the star, we are able to ignore all these cosmological effects, distant galaxies, and we can study the star as if it is located in flat space. Okay, located in flat space. By flat space, what I mean is that all such effects have been ignored, and we are in a situation where there is a vanishing gravitational field. So we are interested in studying the sun. We are at the Earth, and we are assuming that the gravitational field of the sun is dying down sufficiently fast. And when the effects of the gravitational field reaches the Earth, we are in a situation where there is no there is a very small gravitational field, and in the limit, the gravitational field will become zero. So this lead us to study questions related to asymptotically flat spacetime. And asymptotically flat spacetimes are models for isolated systems in general relativity. Okay, and this is the shorthand I will use for the rest of the lecture. GR is general relativity. Okay, so now this is good motivation to study asymptotically flat spacetimes, but depending on the context and the situation that you are interested in, you might be interested in studying other setups. You might be interested in studying asymptotically anti-de Sitter spacetimes. Okay, these are spacetimes which approach anti-de Sitter space as you go far away from the sources. And from the ADS CFT motivation, you might be interested in this, or you might be interested in asymptotically de Sitter spacetimes. Okay, this is a hot topic. This is a topic that some of the speakers in this conference have pursued in recent years. Or you might be interested in asymptotically cosmological spacetimes. So now all these things you might be interested in, but as soon as you start asking questions, you realize that there are key difficulties in defining these notions. What do we mean by asymptotically de Sitter or asymptotically cosmological spacetime? And in order to appreciate this issue, it is good to look at a simple sort of textbook kind of situation, and we ask how general relativity is different from electrodynamics. So it's good to first understand how this is done in electrodynamics, and then we will see what are the problems in general relativity. Okay, so in electrodynamics, there is flat space. Okay, when we study Maxwell's equations, we have flat space, and we are studying electric and magnetic fields on a flat space. And what we study is isolated charge and current distributions. So now, if you want to specify the fall-off rates for the charge or currents or electromagnetic field or electric or magnetic field, what you will do is that you will do the following. You will say that my sources are compactly supported. That is to say, they are sort of located in some finite region of space. And they produce some field, A mu, let's say, and the A mu field produces electric and magnetic field such that the electric field falls off as 1 over r squared as I go to r going to infinity, or the magnetic field falls off as 1 over r squared as r going to infinity. So this is a fixed time. And a field can have radiative part which falls off as 1 over r as r goes to infinity at fixed t minus r. Okay, so this is another notation that I will be using. U is t minus r. So as r goes to infinity, keeping u fixed, then the radiative part of the electric field falls off as 1 over r. Okay, so now at this stage, actually, I will take a small digression and I will introduce this notation, this capital O notation. Okay, so this has a name. This is called the big O notation. So this is a more common notation, and this is what we will be using in this lecture. So what I mean by big O, so capital O, this is math curly letter O, 1 over r squared. What I mean is that this is some constant over r squared plus corrections which are lower than 1 over r squared. So this has corrections C2 over r cubed, C4 over r to the 4, and so on. So for example, if we take the exponential function and we expand it as 1 plus x plus order x squared, what we mean is that e to the x minus 1 minus x has at most errors which are some constant times x squared, mod of x squared. X squared is positive, so this is just constant times x squared. Okay, so this is the notation we will be using. This is what we mean by the big O notation. Okay. Now, the reason I say this because there is a slightly more complicated notation that is used in the literature. This is the small o notation. This is equally common, but it is common for slightly more complicated situation than what we will be discussing in our lectures. This is something we will not cover in this lecture. So this small o notation is very useful. I mean, this is many papers that you will see in on the archive in recent days will have this notation. So small o rho to the minus m, what this means is that limit rho going to infinity, rho to the m times small o rho to the minus m is 0. Because you may say that this is a very small difference, like who cares? Like if you multiply this with r cubed, then it blows up. But if you multiply with power of r, then it goes to 0. So indeed that is true, but there is a crucial difference. The difference is important when you have log terms. And the lot of modern discussion is about log terms. So it is important to understand the difference. So this difference is important when working with log terms. So suppose you have a term in your expansion which is log rho over rho squared. Okay, then in the limit rho times little o 1 over rho will have rho times log rho over rho squared, which in the limit rho going to infinity will become 0 because log rho grows much slower than the rho. So therefore, as a result, when I say little o 1 over rho, I will have log rho over rho. I can allow log rho over rho square terms, n plus 1 over rho square terms, and so on. Okay, so typically if log terms are present, a more careful notion is needed to talk about asymptotics in this context. But for our lectures, we will only be discussing the big O notation. But I wanted to mention that this small O notation is equally common, equally useful, equally important. Okay, the small O notation is a bit more complicated. We will not be dealing with this. Okay, so now let's go back to electrodynamics. Okay, so now you have given me the fall-off conditions for the sources, for the charge density, for the current densities, and you have chosen some gauge maybe for the vector fields such that the electric and magnetic fields are falling off like 1 over r squared at spatial infinity, and they are falling off as 1 over r at fixed values of u as r goes to infinity. Okay, so now if you put that into Maxwell's equations will tell us a great deal about the detailed structure and properties of electromagnetic field at large distances. Okay, and this is something we are taught in our courses. If you have, all of you, I'm sure, have done many of you have taught such courses. So all of you have like done these courses. So these are called the multiple expansions of the electromagnetic field. So multiple expansion of electromagnetic field has infinite set of multiple moments, and these moments are related to multiple moments of charges and currents in a relatively simple way. And this you can do both at spatial infinity, that is r going to infinity limit, or you can do this in the r going to infinity at fixed values of u. This is the dynamical range. So in both these cases, this is a standard material that is taught in the second course in electrodynamics. Okay, so you may ask, okay, why not we teach these things in general relativity? Why? What about GR? Why such things are not taught in a GR course? Okay, there is a good reason for this. And the good reason is that there is a very serious obstacle when you try to do such a thing. So you see, when we were discussing electrodynamics, there was a Minkowski space in the background. Okay, so there was a natural notion of the radial coordinate r, and when we were doing expansions, we were using this radial coordinate r for doing expansion. But when we are in general relativity is a theory which has no canonical choice of coordinates. All coordinates are equally good. So there is no background structure. Okay, since there is no background structure, there is no natural radial coordinate to specify fall-off conditions. Okay, so hence we cannot make immediately, there is a obstacle. How do we make progress in talking about the fall-off conditions and so on? Okay, so the question arises, what can we do? Okay, so this leads to many different approaches which people have taken. And I will discuss this, but before that, I can take some questions. If there are questions or comments.
Till now, there are no questions, so you may.
Okay. Is everything audible? Is it clear what I'm saying?
If there are any quick questions, we may take up now, as Amitabh is saying. Okay, then I think you can just.
Okay, so there are many different approaches. Yeah, thanks, Srijit. So there are many different approaches. So one way around this difficulty is to define asymptotically flat spacetime if there exists any coordinate system x0, x1, x2, x3 such that the metric component behave in an appropriate way at large distances. Okay, so we are not saying that there is a background structure or there is a special set of coordinates. We are just saying there is any sort of coordinates which exist such that in these coordinates, the metric at infinity looks like eta mu nu, and then it has corrections like 1 over r. Okay, and this you can make precise by either looking at spatial infinity or by looking at infinity along the null directions. Okay, so this idea is correct. Indeed, one can do this. And this is adequate in many respects. But it is not manifestly coordinate independent. Okay, if you are coming from geometrical viewpoint of general relativity, then you will be may not be liking this, because it looks like we have to choose some sort of coordinates to make progress on this. Okay, and moreover, it is difficult to specify the precise fall-off conditions as r goes to infinity. And what do we mean by the r going to infinity limit? So making all these questions precise is a bit difficult in this approach. Okay, so to address such concerns, Penrose gave the idea of conformal infinity approach. This is much more popular in the general relativity community because it is geometrical, and one can ask difficult mathematical questions in this approach and address them in a rather satisfactory way. So in this approach, what one does is that one attaches a boundary representing points at infinity to the physical spacetime in a suitable way. Okay, so the exact gluing conditions are a bit difficult to explain, but you think of it roughly that you take your spacetime, you have a boundary at r going to infinity, and you attach this boundary in suitable way to your spacetime. Okay, so such an approach is mathematically speaking very clean. One can do a lot of calculations with this, but doing calculations in this is difficult because you have to talk about the physical spacetime and the unphysical spacetime. The unphysical spacetime is the one where you have attached the boundary, and then you have to talk about how this gluing happens and so on. This is very good, but it has some limitations. So one limitation is that doing calculations is difficult, and difficult to bring the richness that the coordinate-based approach gives you. In coordinate-based approach, it is difficult to specify boundary conditions, but once you specify one set of boundary conditions, you can change them. And that way you can analyze multiple things, and it's a very rich setup. I'm not saying that this approach is not rich, but it's difficult to bring out this richness of the coordinate-based approach in such a simple way in this approach. Okay, at least this is how I think about it. Okay, so let me make a summary of various approaches that people have. Okay, there are many approaches. These are some of the most popular approaches. Okay, so popular approaches based on coordinates or based on geometry. So at null infinity, the coordinate-based approach is called the Bondi-Sachs. The geometrical approach is called Penrose conformal infinity approach. At space-like or time-like infinity, the coordinate-based approach is called the Weik-Schmidt approach. They were the first people to introduce the right set of coordinates to analyze this. There are other approaches, but this is the one that is quite popular. And there is a geometrical approach because of Garrosh at space-like or time-like infinity. Okay, so now what people have been doing in the last few years is trying to unify these approaches. So when you want to unify space-like or time-like infinity to null infinity, what you have to do, you have to relate the Weik-Schmidt approach to the Bondi-Sachs approach. And similarly, when you want to unify the Garrosh's approach to Penrose's conformal infinity approach, you have to do some sort of mathematical gluing of these things. Okay, so these things have been studied in the literature. Unified frameworks, what this means here is the explicit coordinate relations between fields in the Weik-Schmidt approach to the Bondi-Sachs approach. And what here it means is this matching of the mathematical structure. Okay, so this is what Professor Abhay Ashtekar started during his PhD time, and he has pursued this over 40 years. Recently, he has written some papers also in which the unification is done. So this is a sort of hot topic. Like there are lots of papers coming out on this unification and relating various coordinates and various geometrical approaches in this. Okay, so
there is a question, Amitabh.
Yes,
You may probably take up. So this is by Neeraj Kumar. Does choosing a particular coordinate mean choosing a specific observer? So probably it's related to the coordinate-based approach.
Yeah. One can think of it like this. So maybe one can say that choosing a particular coordinate at infinity means a particular time direction and particular space direction. So observer, you have to say the observer is static at infinity, so the axes are not changing. and time is not changing. I mean, time is moving in the standard way. So that will define the notion of time, and that will define the notion of axis and so on. So indeed, they are related. Yeah. Okay. So, so I have been asked to teach the Bondi-Sachs approach. So you see, I am only teaching this corner. But as you can see, there is this big literature. So Bondi-Sachs approach is tied to coordinates, okay, as we emphasized earlier. Okay, so because it is tied to coordinates, some of the math issues are difficult to address. Okay, if you want to ask what is the mathematical questions, how it looks in the geometrical approach and so on, those questions are difficult to address. Okay, but historically, this analysis has provided a very convincing analysis of the energy carried by gravitational radiation. Okay, this is why Bondi was knighted, and the paper is so famous and so on, is because this was the first analysis that gave the convincing analysis of the energy carried by gravitational radiation. The biggest advantage of this approach is that the approach is very hands-on. Okay, you just have to work hard. You will set up the coordinates. The expansion of the in those coordinates, expansion of the metric will be given to you. You just use Einstein's equations, compute gammas, compute Riemann tensor, Ricci tensor, and it's just a very hands-on approach. Like anybody can start working on it with just few. After you have finished a first course in general relativity, one can start working on this approach. And because it is very hands-on, one can program this and one can do various things with this. And this is what my colleague Sitinder will be telling us in later lectures. So much of the modern day research is done in the Bondi-Sachs formalism. And let me just, before I go into the technical points, let me just say that there are, like, these are the type of problems that people are discussing in the modern literature. So Professor Beatrice Bonga will give talks in this conference, last talk. She has worked a lot on Bondi-Sachs formalism in De Sitter. There is a lot of discussion about unified formalism going from spatial infinity to null infinity. So coordinate versus unified Ashtekar-Hansen formalism. So this is something that is a lot of people have discussed in the recent years. In the original paper, the focus was only at spatial infinity by Ashtekar and Hansen, but more modern work has been trying to relate this Ashtekar-Hansen first to coordinates in Weib-Schmidt coordinates and then to Bondi-Sachs. So there are many papers. So these are sort of two examples of hot topics which are being discussed a lot in the.
So there is a question by Samik Datta.
Yeah.
He is probably clarifying in this Bondi-Sachs formalism, is the general covariance of GR violated?
Is violated in the sense that we are choosing a special set of coordinates. We will do a complete gauge fixing, but since we have made a choice of coordinates, this is indeed a violation of general covariance, if we can put it that way. But in the Penrose's approach, there is no violation of general covariance. All questions are asked in a geometrical way, and all questions are answered in a geometrical way. So in that sense, that approach is more covariant, if you wish.
Let me just ask one question related to this. So in the Penrose's approach, all questions can be answered in the geometrical way, but that requires that something is happening at the sky plus itself. I mean, the artificial boundary that needs to be added, right? So I mean, physically, I think the other approach is more illuminating, isn't it? I mean, somebody is reaching the null infinity, having some fall-off, particular fall-off, rather than somebody actually at the null infinity, at the conformal completion of the space-time and doing something.
Yeah. No, this is why they made a distinction. There is a distinction between the physical space-time and the unphysical space-time. Unphysical space-time is where the boundary is attached at a finite distance. And physical spacetime is the spacetime in which the boundary is still at infinite distance. You go back and forth and try to convert calculations from unphysical to physical and things like those.
Yeah. And the structure will not be always identical. If we do analysis from these two different perspectives, so we bound to get some differences.
Yeah, of course. Because you are doing conformal transformations, even the wild tensor or the Ricci tensor, all those things will change. I mean, the geometrical properties of unphysical spacetimes are very different from physical spacetime. But the advantage of the approach is that it's completely geometrical. That's why the approach is attractive.
Yeah, I will ask you more about this and later. So let's.
Okay, yeah, so the Bondi-Sachs. Okay, so now we have sort of decided that we will work with Bondi-Sachs, and I have listed the context in which we are working. We are only working at null infinity in asymptotically flat spacetimes for this lecture at least. And we see that there is this geometrical approach and so on. Okay, so this is a very active field, and the reason this field is active, the way I see this, is that there is a lot of art here. So, Srijit, for example, wants to work on a project, and he would say that what he finds interesting, he will decide some sort of boundary conditions based on what he finds interesting, and some other person will find some other thing interesting, and some other person will design boundary condition based on what the other person finds interesting. So because there is a lot of freedom in choosing what you find interesting, I would say this is some sort of art. And then you do this full analysis and you reach the science, and it's a balance between what you allow and what you get. Okay, so what you find interesting, the formalism gives you the freedom to do that, and this helps you answer what sort of questions you want to address. Okay, and so one can write in some sense an infinite number of papers on this subject, because you can always play with there are too many things to play with. Okay, so let me explain how this all this comes about. Okay, so what we are interested in is gravity in Bondi gauge. So what we will do is that we want to define asymptotically flat spacetimes which approach the notion of future null infinity. Okay, because the Bondi-Sachs formalism is at null infinity, so we want to approach null infinity. The full Penrose diagram of flat space is this. On the leftmost side, you have I plus, time like infinity, scribe plus, future null infinity, I0, space like infinity, scribe minus, future past null infinity, and I minus, which is past time like infinity. Okay, so what we are interested in asymptotically flat spacetime. So we remove the interior region. So then we have only the boundary left, and the interior you can fill the way you like. So again, you have so many things like future and past, time like infinity, space like infinity, future and past, null infinity, all these things you have. The Bondi-Sachs formalism only allow you to address the scribe plus or the scribe minus. Okay, only at future null infinity you are doing your analysis. If you want to relate your analysis from future null infinity to space like infinity or future null infinity to time like infinity, then you have to do other things. Okay, that is this Bike-Schmidt kind of approach, but the Bondi-Sachs formalism will only allow you to do analysis at null infinity. Okay, so this is what we are doing. So we are only studying radiative nature of spacetimes at null infinity. This is what Bondi-Sachs is about. So physically, we are in the radiation zone where gravitational radiation is coming, where gravitational waves and other null waves phenomena is happening, and these phenomena are leaving some imprint of the space-time dynamics because of sources or because of whatever is happening in the space-time. Black holes may be colliding, some explosion is happening. All of that is coming at null infinity, and the Bondi-Sachs formalism is providing you information about what happened in the interior of the space-time. Okay, so this is how this thing is done. Okay, so now what we will do is that we will choose specific coordinates. So we choose coordinates x mu to be u r theta phi. Okay, u is t minus r. So u r theta phi. Then what we will do is that this is a fully gauge fixed formalism. Okay, so diffeomorphism invariance, general relativity has 4 coordinate transformation invariance. Because there are 4 coordinates, you can do 4 transformations. What we will do is that we will fix all these 4 coordinate transformations. Okay, so the way we will fix this is the following. So we will say the metric in Bondi gauge takes this form: G mu dx mu dx nu. This is the general metric, has UU component. Okay, so my coordinates are U R theta phi. The metric has UU component. The metric has UR component. The metric has UA component. The metric has no RA component. Okay, all the RA components are set to 0, and metric has GAB component, where AB are the indices on the theta and phi directions. Okay, so this is how the metric looks like. So the metric has GUU component, metric has GUR component, GUA component. So the first line is completely non-zero. It can be non-zero. Then this 2 by 2 block is completely non-zero. This 2 by 2 block is G theta theta, G theta phi, G theta phi, and G phi phi. But then these 3 things have been set to 0. So GRA has been set to 0 and GUR has been set to 0. Okay, so the second line, all 3 things have been set to 0. Is this clear? So GRR has been set to 0 and GRA has been set to 0. So these are the 3 gauge conditions. And the 4th gauge condition is that the determinant of the 2 by 2 metric on the sphere. So this is a metric on the sphere, G theta theta, G phi phi, G phi phi, G theta phi, and so on. So the metric on the sphere has been set in such a way such that the determinant of this metric is R squared times some function of theta and phi. So this determines the function R. This product, this determinant must be R squared times some function of theta and phi. So these are the 4 gauge conditions. And when you impose these 4 gauge conditions, you get metric in Bondi gauge. Okay, so now you might say, what are the examples? Okay, so the flat space is one very simple example where you write the metric as minus dt squared plus dr squared plus r squared d omega squared, and just use u equal to t minus r. If you use u equal to t minus r, then you will get the metric in Bondi gauge. Because it's a diagonal metric, no, only cross term that will appear is because of t minus r. So ur term will appear, everything else will be 0. Now, all of you have studied one more example of this. This is Schwarzschild solution. Schwarzschild solution you study in outgoing Eddington-Filkenstein coordinates. Okay, remember so first you go from tr theta phi to tr star theta phi, and then you go from tr star to ur star theta phi. So ur star theta phi or ur theta phi coordinate is an example of Bondi coordinate because again it has only these components.
Amitabh, there is a question from Sanket Thakkar.
Yeah.
So, what is the reason behind choosing this gauge? He's asking about what are the physical intuitions?
So this I will explain in the next slide. Okay, but okay, so let me say one important comment here. Okay, so this Bondi-Sachs formalism was not developed overnight. Okay, like Bondi-Sachs and various people, they wrote many papers over many years, and after a very detailed analysis and lot of confusion, they converged on this formalism. It's not like this whole thing was developed in one paper. There was a huge amount of confusion about what is a good boundary condition, what should be the good gauge choice, and so on. But after all these papers sort of settled down, this is what people came up with. So it's not like one can justify this in one sentence. I mean, this is a I mean, you may ask why this is a good method of analyzing this. I mean, there is no one sentence answer to that. Many papers were discussed, were written, and then people converged that this is a good sort of way of analyzing everything. Yeah. Okay, so yeah, but the specific question I can answer. The specific question is, what is the physical meaning behind these coordinates? Okay, so here is a slide that I try to answer this. So these coordinates are based on null hypersurfaces. Okay, you want to study null infinity, so it's natural to work with null hypersurfaces. So these null hypersurfaces are labeled by constant u coordinates. Okay, so here is your null infinity, what I call stripe plus, and you draw these null lines which reach your null infinity. Okay, so each of these lines is u equal to constant null hypersurface. Okay, so because these are null hypersurfaces, u equal to constant is a surface whose normal is null. So what that means is that GUU, because this is what you will do if you want to calculate the norm of the normal, you will G mu nu, N mu, N nu, and N mu is just in the direction of u. So what this means is that GUU is 0. Okay, because normal is N mu is G mu u, which is because G mu nu del nu u. So if you take this derivative has only u component. So you will get G mu u equal to 0. And since the normal is null, you will have the condition that G u is 0. Okay, so this is one way of justifying one condition. The other condition is that you say that the angular coordinates are such that moving along the normal, this n mu normal, the axes do not change. Okay, so you have a normal. Now using that normal, you can draw curves, and the idea is that something bad happened. Yeah. So the idea is that if you draw that curve, then the xa coordinates do not change. That is to say, n mu del mu of theta is 0. And so if you move along the n direction, the theta and phi coordinates do not change, but theta and phi are coordinates. So what this means is that n theta and n phi components are 0, which essentially means that g theta u and g phi u components are 0. So if you take g u equal to 0, g theta u equal to 0, g phi u equal to 0 based on these physical requirement and invert this metric, then you will see that when you invert this metric, you will get the metric to be of this type, that GRR is 0, GRA is 0. Okay, and in the inverse metric, the conditions are GUU upper is 0 and GUA is 0. So there are 3 conditions there, 3 conditions here, and the determinant is fixed by this R squared. Okay, so this is what this is the best I can say about the physical meaning of these coordinates. Does that answer your question? Partly, at least.
Yeah, you may continue if some more questions appear. I will read out.
Okay.
So
So
there
yeah.
there is one more question by Ritapriya Pradhan.
Yeah.
He is asking that, can you discuss how to go to Bondi gauge starting from an arbitrary coordinate, and
Yeah.
how to derive the coordinate transformation, and what about the residual gauge freedom? Do we have any?
Yeah. Okay. So you see, these are very important questions. Actually, I must say it is not easy. If you give me a metric, Kerr metric, for example, Kerr metric has G theta phi, G T phi component. And if you want to go from Kerr metric in Bondi gauge, then you have to struggle a lot. It's not easy. In general, given a interesting metric in standard set of coordinates that you study in your textbook, it may be very difficult to go to Bondi gauge. Okay, that is not at all easy, especially for rotating metrics. Now, residual gauge degrees of freedom. So if you can put the metric everywhere in this form, then all the coordinate freedoms have been fixed because you have used 4 gauge conditions. But that may not be easy. So what you may be able to do is that you may be able to fix this form of the metric near infinity and may not be able to fix at other places. And then you have residual gauge degrees of freedom left. Another possibility is that if you bring the metric into this form, but these functions, the functions that are appearing in the metric, if they have some sort of ambiguity, then again, there is a residual gauge freedom. This freedom we will discuss in the next lecture. That leads to the concept of asymptotic symmetries. So just to answer your question briefly, that it may not be easy to bring a random metric into this form. Okay, so even the Kerr metric is quite difficult. Okay, but as you can see, these are just coordinates, these are gauge choices, so it should be possible. Okay, so far we have not done not much. So far everything is geometry. And we have Minkowski spacetime, which is minus du squared and du dr and r squared gamma ab dxa dxb. So this is certainly in Bondi gauge. Okay, so what do we mean by asymptotically flat spacetimes? Okay, these are the definitions now. So now, since Minkowski space has this property that GUU goes to -1, it will be natural for you to guess that I will call a spacetime asymptotically flat if in the limit r going to infinity, GUU goes to -1. Okay, this will be a natural definition to try. And similarly, GUR has to go to -1. And since there is no cross term, you may say that GUA is 0. And you may say that the metric on the sphere coordinates goes to r squared times gamma ab. So this is what will be your natural guess. Okay, this is what you would say, that GUU goes to -1, GUR goes to -1, GUA goes to 0, and GAB goes to r squared gamma ab, where gamma ab is the round metric on the sphere. Okay, so as I was saying, it was not in one paper that this analysis was done. It was like hundreds of papers. But Bondi-Sachs, when they wrote their 9th paper, they sort of converged on the exact boundary conditions that they want to work with. So it's not easy to justify what I'm saying next in one talk or one sentence. Okay, but this is what they showed. So after a very detailed analysis over many years, over many papers, the following boundary conditions were proposed. So the boundary conditions are very similar to what we're discussing here, but these are...
sorry, Amitabh, to interrupt. I think Bondi and Sachs didn't write a single paper. Sachs wrote his own
yeah,
paper.
sorry. Yeah. Sachs wrote a separate paper and Bondi and other people wrote
Others.
it. Yeah. Okay, thank you for this historical remark. Okay, so the boundary condition that they came up with is the following. So GUU is -1 indeed, and it approaches 1 over r in this big O notation. So GUU is -1 plus order 1 over r. Similarly, GUR approaches -1, but at order 1 over r squared. Okay, so there is no 1 over r corrections here. GUA, so this you might think that GUA is 0, but this is not what turns out to be good. Equations of motion do not turn out to be consistent. GUA should be something constant. It does not grow with any power of r. This is what they found. GUA must be order r to the 0. And GAB is, as we guessed earlier, it should be r squared times gamma AB plus some correction, which is 1 power less. So 1 power less. So this is going as r squared. This correction goes as r. Okay, so now you might say, why should I believe this? Why this is interesting? Why should I care? Okay, there are many reasons. These boundary conditions need to ensure that they lead to good definitions of conserved charges. You must be able to say, what do I mean by the energy of gravitational waves? You should be able to say that the dynamics on such dynamics with such boundary condition does not lead to any infinity of any type. It should not happen that if I try to calculate the mass of a space-time and I find an infinite answer. Okay, so this is the art. So now you have to come up with the boundary condition which allows you to do the physics that you are interested in, which allows you to do study, coalescence of two black holes, for example. But you cannot impose a very restricted boundary conditions which does not allow, let's say, for gravitational waves. You want to allow gravitational waves to come out. So this is what I meant, art and science. So you have to have definitions which are weak enough to allow rich enough dynamics, but restrictive enough to lead to good physical answers. Okay? You cannot have things going like r to the 3, for example, here, or things going like order r here. Because if you do that, then the mass will diverge, or angular momentum will diverge, or something of that type will happen. Okay, so this is where the art and the science balance is there. You have to allow boundary conditions which are restrictive enough to give you physical answers, physically sensible answers, and general enough so that you discuss the dynamics that you want to discuss. Okay, so we cannot be too general, we cannot be too restrictive. So this is the balance that you have to achieve, and during this balance, one can write many papers and achieve this. Okay, so now now let us discuss the full Bondi metric. Okay, so this was the so what I discussed above is the asymptotic metric, but now we have to write the full metric, which is like this full metric in this form. So this metric is written in this way. So this is the form, these 3 lines. So this is the metric in Bondi, general metric in Bondi gauge. Any metric can be brought into this form. The GUU component of the metric is e power 2 beta times capital V over R. So beta is a function, capital V is a function, R is the coordinate, and this is the whole thing is the UU component of the metric. Okay, so far there are no assumption. Beta is a function of U R theta phi. V is a function of U R theta phi. The only thing I am saying is that I will parameterize my GUU component in this way, e to the 2 beta V over R. You might say why this is useful. Again, there is no one sentence answer to this. If you do the analysis, you will find that this is the most useful way of doing this. Yeah, this is the reason it has been done like this. It's like the ADM formalism. You see, the ADM formalism was not developed in one day. ADM wrote like 8 papers in 1 year, and then they came up with the correct with the ADM formalism that we study in our GR course. Okay, so now look at the UR component. The UR component is e power 2 beta minus 2. So the UR component you parameterize with this 2 power e power 2 beta. Okay, and the theta phi components you parameterize in this way. So this is theta phi, theta phi, phi phi, and these are the coordinates. And then there is this UA function that appears. So UA is a function which sort of determines the cross terms between dxa and u. Okay. So let me stop here for a moment to just make sure that everybody is with me in terms of the functions.
So there are 1 or 2 questions.
Okay, yeah, I can take the questions. Yeah. Why
So
there is no R term in the...
yeah.
Again, yeah. So this is motivated by finiteness of various quantities. Yeah, indeed. Finiteness of angular momentum, finiteness of mass and things like this. Yeah.
So
Okay.
these choices of boundary conditions, probably somebody is asking that whether these choices are unique.
No, as I said, so this is a balance between art and science. Okay, you allow your Bondi-Sachs. This is what those boundary conditions and the precise analysis that I will discuss later. This is what these people came up with. After that, the paper has more than 2,000 citations now. After that, many people have tried to relax those boundary conditions in various ways. In trying to relate to space like infinity, in order to generalize this to other setup, in order to have scalar fields in the space-time, vector fields in the space-time. So it's a big subject. I mean, you change your boundary conditions such that physically everything makes sense and is restrictive enough so that you don't get infinities of various types. Yeah, there is one more question about gauge choice motivated by Vaidya solution, as in Eddington frequency and coordinate metric look there. No. The gauge choice is not motivated by Vaidya solution. I mean, the work of Bondi-Sachs was, I mean, it's an example. It's not motivated by that. The Vaidya solution, you can think of it as an example of a metric in Bondi form with some matter. Okay.
Also, one question
Yeah.
that was asked by somebody. Shivam Kumar Misra. Does this formalism ease singularity problems also?
Oh. Yeah. So, okay. So as I was saying, it's difficult to write if you just take Kerr metric, it's difficult to write Kerr metric in Bondi form. Okay, this exercise itself is very difficult. Now, once you do that, then the singularities of the curve solutions are indeed there in this metric, but additional spurious singularities may show up. What typically what happens, what you find is that this UA function has 1 over sine theta kind of singularities. So the approach has issues with the singularities. Yeah, so it's not like singularities go away. In fact, more singularities can appear. But again, these are not unique choices. I mean, there are this we will discuss in the next lecture. There are some ambiguities in these functions. These are called asymptotic symmetries, and those ambiguities can be used to fix those singularities in a way.
By singularities, you mean the singularities at the asymptotic regime, right?
Yeah, so asymptotically, you can make things regular. But if you write, let's say, curve metric in standard Bondi-Sachs coordinates, you may find that the function UA has 1 over sine theta kind of behavior. So it has additional, if you wish, additional singularities at theta equal to 0, theta equal to pi.
Okay.
But those are not physical singularities. You can get rid of them.
So coordinate.
Yeah, coordinate issues. Yeah, coordinate. But the coordinate issues are related to the choice of UR theta phi. You can change UR theta phi in slightly allowed ways such that the form of the metric does not change.
Okay, thanks.
Hi, Srijit. Can I clarify my question?
Yeah, yes, Neeraj.
Amitabh. Yeah, so I'm saying once I decide the boundary conditions and once I'm in a particular gauge, which you mentioned, and then I put the condition of all the charges to be finite.
Yeah.
Then I end up with the boundary conditions, right?
Yeah.
Right. The structure of G mu, G UU and all. So the structure I'm going to get at this point will be unique. That's what I'm asking. The boundary condition is already chosen and fixed, suppose.
Yeah. So the fall off is fixed. Yeah, this is what you will get. But now there are additional freedoms. So these are asymptotic symmetries, which I will discuss in the next lecture. The asymptotic symmetries will preserve these boundary conditions, but change your functions.
Okay.
Yeah, so by that you can have additional issues in theta direction, in phi directions, and things like those. Yeah, in the R directions, you have fixed your boundary conditions. We agree on that. But in the U, theta, and phi direction, there is some freedom left. No, so that freedom can create problem.
All right. Thanks.
Okay, so now I hope the counting is working. So you see, let us go back and see the counting. So you see, so this component is beta. This is e power 2 beta. This component is V. This component is UA. So U theta, U phi. And these 4 components are G theta theta, G theta phi, G phi phi. Okay, and everything else is 0. So these are 0. And so we have function for each component. So it's not like we have restricted ourselves to anything. So now we specify our boundary conditions. So the GAB, which is metric on the sphere, we expand like this. So GAB is R squared gamma AB. Gamma AB is the round metric on the sphere because we want our space-time to approach Minkowski space. So gamma AB is round metric on the sphere. Then it will have corrections. Corrections are of order 1 over R. Then next correction 1 over R squared. Next correction 1 over R cubed, and so on. Now, remember, one of the gauge condition was that the determinant of GAB should be R squared, a function of theta and phi. Actually, I should have said something more. This is function of R squared times sine theta, because the gamma AB has a sine. This is a typo. There should be a sine theta here, because round metric on the sphere has determinant sine theta. So the determinant of GAB is R squared sine theta. So this is the gauge condition you want to impose. So if you impose this gauge condition, then there will be trace conditions on this C, D, and E. So what will happen is that the conditions for D and E are a bit difficult to write, but in this lecture, I'm only discussing the C. So the condition on C will be that it is traceless. Gamma AB, CAB is 0 because of the determinant condition. Okay? So the determinant of the full metric is fixed to something that is given by the leading part, and then the remaining should be trace-free. So gamma AB, CAB is 0. Okay, so this CAB is the most important quantity in Bondi-Sachs formalism, and we should really understand this CAB, and this is one of the last set of slides I have for today's lecture. So CAB is a symmetric traceless tensor, which is arbitrary function of the retarded time u and the angles. Okay, because the expansion in powers of r has already been done. So only u, theta, phi are remaining. So CAB is a function of u, CAB is a function of theta and phi. And since it is traceless, it has only two degrees of freedom, symmetric and traceless. So it has c theta theta and c theta phi. So CAB is a symmetric traceless function, arbitrary function of retarded time u and the angles. It has only c theta theta and c theta phi. This is the function, this is the tensor function that captures everything about radiative fields. Okay, it contains, because there are two functions, it contains information about the polarization of gravitational waves, and it contains everything that you want to know about gravitational waves. Everything will be constructed out of these functions, c theta theta and c theta phi. Okay, so this brings me to the quantity that people discuss a lot. This is called the Bondi news. So the name will become clear in a moment. The definition of Bondi news is derivative of the C function. So NAB is partial U derivative of the function CAB. CAB is a symmetric traceless function on the sphere. Its derivative is NAB. Okay, so the physics is the following. Whatever dynamics is happening in your space-time, okay, black holes are colliding, or star is exploding, or something, whatever is happening, CAB is the imprint of all of it. CAB has the information at null infinity what happened in your space-time. It brings to the null infinity the news about what happened in the space-time. Okay, news in the sense that the imprint of what happened in the space-time is at null infinity. That's why it's called the news tensor, or the Bondi news, or Bondi news tensor. It has three different names: news tensor, Bondi news tensors. At far distances, this is what is telling you about the what happened in the space-time. Okay, so now we ask what are the other. So you see, so this is what I explained about the GAB. So this is about the GAB, but there are other functions, no, V and beta and so on, and U and so on. So we have to tell what is the asymptotic behavior of these functions. Okay, so the U I will discuss in the next lecture. Here I am discussing only beta and V. So the beta function goes to 1, and then it has no 1 over r term. This comes because of some equation of motion analysis, which Sitinder will explain when he discusses how to program all this in Mathematica. E to the 2 beta has 1 plus order 1 over r square. It has no 1 over r term. This comes because of equation of motions. And the V function starts with minus r and has some correction which does not go with any power of r. And this has capital O, these are all big O notation, has correction which is 1 over r. So as a result, if you multiply these two things, what you have is e to the 2 beta times v over r is minus 1 plus 2m over r. Okay, so this m is a function of u and xa. Okay, this is the very important, the second most important function in the Bondi-Sachs formalism. The first most important function was the CAB tensor, Bondi news. The second most important function is this Bondi mass. So this little m is a function of u and xa. This is called the Bondi mass aspect. Okay, it gives, this is a function of u, theta, and phi. It gives you information about the mass of the spacetime as it is distributed in angular directions. It gives the angular density of the energy of the spacetime as measured from a point at null infinity. Okay, so if you want to calculate the full mass, the full Bondi mass at any value of u, what you have to do? You have to do integral over the xa coordinates. So you go to the sphere at infinity, d2 omega m times u times u. Go to the sphere at infinity, do the integral over the angular coordinate. This will give you the total Bondi mass, capital M of u. Okay. Okay, so now this I will not be able to explain. This is really the magic of Bondi-Sachs formalism. With some more hard work, one can show that the derivative of capital M of u is negative. Okay, one can show this using equation of motion analysis. And physically what this means is that radiation carried away by gravitational waves escapes null infinity in such a way such that it always lowers the energy of the spacetime. So if you have mass of the spacetime at u1 and mass of the spacetime at location u2, the radiation will carry away always positive energy. So mass at u2 is always less than mass at u1. Okay, this is very important. Mass at u2 is less than mass at u1. Mass in the u going to minus infinity limit will match the total mass of the spacetime. This is called the ADM mass, the total mass of the spacetime, ADM mass. So you see the Bondi mass aspect is playing a very important role. It is telling us about the decay of the Bondi mass aspect, is telling us about how much gravitational radiation is coming out in which direction, how much energy is coming out in which direction. The Bondi mass equates the ADM mass at spatial infinity. Okay, so now let me summarize whatever we have discussed. I'm a little over time. So whatever we have discussed is the following. So we have flat space minus du squared minus du dr and r squared gamma ab dxa dxp. The first line is just flat space. And then in today's lecture, we have discussed two corrections to this. The first correction is this du squared term. This is the Bondi mass aspect. And the second correction is this Bondi-News term, or the CAB term. This is r times CAB dxa dxp. And then, as I was telling you earlier, the equations of motion will not allow you to set this field to 0. Okay, earlier I was saying this UA term, the equations of motion will not allow you to set this to 0. Okay, so then you will get a term. And that term is this divergence of CAB. So CAB is here, which grows with power of R, but then there is a cross term, and this cross term is the divergence of CAB. So this is what we have discussed in today's lecture: Bondi mass aspect, the News tensor, and then the equations of motion will force you to have this divergence of CAB. Okay, the subleading terms we will analyze in the next lecture. So with this, I will stop.
Thank you, Amitabh, for the first lecture. So it was very nice and lucid. So now we are ready for questions and discussions. We have
Yeah,
time,
so we
5 minutes.